So earlier I told you from your worksheet, don't do chromium or copper because, all these rules that we've talked about with electron configurations, there's actually an exception to these two. So I have the noble gas or the abbreviated electron configuration for you there for chromium and copper. And that's what we would normally do. We would take argon because that's the noble gas that comes before it. And then we would start at 4s, put 2 in 4s, and then 3d4. But that's not actually correct. So there's something very stable about having a half-filled D subshell. So instead of having 4s2, 3d4, it's more stable to take a 1 out of the S and put it into the D. So then we get 4s1, 3d5. So we only are going to do these exceptions for chromium and copper, nothing else. So I don't want you to start taking out of the S and putting it into the D. This is only for chromium and copper. So copper, instead of a half-filled D subshell, we get a fully filled D subshell. So again, those metals, those transition metals, are all about having a half-filled or fully filled D subshell. So only do that for chromium and for copper. Okay, so we were looking at previously, we said that the groups have similar electron configuration in their endings. So here's that again. So that's why they have similar properties. So alkali metals are all very reactive because they only have that one electron, that one valence electron. Halogens are all very reactive because they have 7 valence electrons. Then group 2 alkaline earth metals are not very reactive because they have 2 valence electrons. And then noble gases are not very reactive because they have 8 valence electrons. Well, except for helium. Helium only has 2. So the properties are similar because the electron configurations are similar. Okay, we're going to cover just a few periodic trends. First is atomic radius, so the size of the atom. And the trend is as we go left to right across the period, the atom size decreases. Now I want to talk about this because lithium only has 3 electrons. So we get 1s2, 2s1. Fluorine, has 9 electrons. So we get 1s2, 2s2, 2p5. So based on the trend, because we're going, let me just show you here, across the period, lithium over here in 1a, fluorine in 7a, and lithium is bigger than fluorine. So normally when I have more of something, I would think, well, that's going to be bigger, but that's not the case. So not only does fluorine have 9 electrons, it also has 9 protons. So there's kind of the game changer right there. Lithium only has 3 protons. So it's not able to pull its valence electron in as close. But with fluorine and its 7 valence electrons, that positive 9 charge in the nucleus is able to pull those electrons in closer. Now going down a group, you can see that the size of the atom increases. This one makes a little more sense. Okay, so lithium to sodium. So 1s2, 2s2, 2p6, 3s1. So we're going from an ending of 2s1 to 3s1. So 3 is a higher shell number. And remember we said anytime you get into a higher shell number, you're getting further away from the nucleus. And so it's going to get bigger and bigger. So going down the group, the atom gets bigger. Going left to right, the atom decreases. So that's the general trend. Okay, for ion sizes, So cations, cations are positive ions, right? Because they lose electrons, and so it makes their overall charge positive. Cations are always smaller than their neutral atom. So there you have lithium in the middle as an example. So you have lithium atom, it loses one electron and it goes down to lithium ion, and you can see it's much smaller. And then the other example is iron at the bottom. So iron atom is the first one, and then we lose 2 electrons, it gets smaller, and we lose another electron, it gets even smaller. So cations are always smaller than their neutral atom. Anions are always larger than their neutral atom. So for fluorine, that very first example, fluorine is really small, but then when we add an electron, the fluorine gets much bigger. So just remember, anions are always bigger than their neutral atom. Cations are always smaller.